Hello class. The purpose of this video is to help you understand the meaning of the average atomic mass. What is that number that's underneath each element on the periodic table? And so I have an example here of carbon, and I can see my average atomic mass is 12.0107. What does that mean? The average atomic mass is the weighted average of all the atomic masses of all the isotopes of that element. Okay, and so we have learned that different isotopes are versions of the same element that have different numbers of neutrons. A good example of this is hydrogen. Here you can see the example. This first hydrogen, which has, we give it a special name, protium. They're all versions of hydrogen. So this first one has 0 neutrons, and so it has a mass number of 1. Deuterium, which is, or hydrogen 2, has a mass number of 2. And then this third isotope, tritium, has a mass number of 3. All hydrogen, and you could call them hydrogen 1, hydrogen 2, hydrogen 3, but different mass numbers. They all exist in nature, but if you look on the periodic table and look underneath hydrogen, it says 1.008. That tells me that by far the most abundant isotope is this version, because it has a mass number of 1, and if we average them all together, considering abundance, then our average is really close to 1. Same thing with carbon, where our average is very close to 12, but is not quite 12, a little more than 12. Let's take another look with a simulation here. I've got a PhET simulation pulled up here. Again, you can see we can construct different isotopes, in this case of carbon, and so I can say, okay, this is carbon 12, there's carbon 13, and those are the same element, different mass numbers. If I look at nature's mix of, we'll switch to carbon here. If I look at nature's mix of carbon, I see that the purple dots represent carbon 12, 6 protons, 6 neutrons, by far the most abundant version of carbon. There are, however, these green dots, which are carbon 13, and that's carbon with 6 protons, 7 neutrons, and there are still some of those, but not near as many. And so if I were to average them all together, considering abundance, then my average comes out to be 12.01. That's my average mass. If we look at another example, let's see if we can find another good example. Here's neon. Neon has 3 naturally occurring isotopes. We've got neon 20, 21, and 22. Those are the different mass numbers. I can see my most common isotope of neon is this neon 20. And so I can expect, and that what we see is that our average is very close to this 20. Just one more example. Say, let's find one where it's a little closer to in the middle of the nice array. This is a little closer. Chlorine has 2 naturally occurring isotopes, 35 and 37, and they're a little closer to being evenly dispersed. They're not even. Chlorine 35 is most abundant at roughly 75%, and then roughly 25% is chlorine 37. And so when I average those 2 masses together, considering abundance, I get 35.45. Now, how do we do that calculation? I'm just going to give you a brief rundown. We'll talk about it more in class. We'll do some practice. Here is a short slide on how you would calculate the average atomic mass. Here is the general formula where you get the, let me see if I can fix my video. Yeah, it works. Half my face. Boom. You can see the general formula. It says to calculate the average atomic mass, multiply the abundance of each isotope times its mass and find the sum of these values. And here's our general formula. This little symbol here means the sum of, and so we're going to add up all of the abundance times masses for each isotope. Our example here is copper 63, copper 65. And so I see that 69% of my copper atoms are copper 63, and the rest are copper 65. And so that the difference between 100% and 69.15% is 30.85%. And we'll see that in our calculation. Find the average atomic mass of copper. Here's how I would set that up. First of all, my percentages, my abundance, I have to change into a decimal. And so instead of 69.15%, I would change it to a decimal down here, 0.6915. That's the abundance of my copper 63. My mass of copper 63 is 62.929. Now that's a little confusing. It gets into a little. So why is the mass different or less than the mass number? It has to do with the nuclear binding energy and Einstein's E = mc squared equation. Feel free to look that up on Wikipedia. Some light reading for you. Let's just for now accept that this is the atomic mass of our copper 63. Okay, now I multiply my abundance of my first isotope by the mass of my first isotope, and then I add the abundance of my second isotope multiplied by the mass of my second isotope. If I had a third isotope, I would multiply the abundance times the mass. This is actually how your weighted grades are calculated. I multiply the weight of the section, tests, labs, homework, by the score that you have in that section, and add them all up. Okay, and what I would end up with is the average atomic mass for copper. I'll let you plug that in if you're interested, but that's how you would calculate it. We'll get some practice with that in class, but that is average atomic mass and what it means.